So now we are going to go to the other type of chemical bondings, which is covalent bond. So go to a covalent bondings. Covalent bondings. That's B. Covalent bondings. A covalent bond is simply an electrostatic force of attraction between the positively charged nuclide and the lone pair of electrons, or the bonded pair of electrons, or the participant pair of electrons. Example, let's say we have two elements A and B. So here is A, here is B. Between A and B, there's an intersection. So that intersection, we are going to have the electrons of A, the electrons of B. Let's say we are taking an X or a cross for A and a dot for B. So these are the electrons. A and B are sharing their electrons together. So in a covalent bond, actually, we don't have like a complete transfer of electron from metal to non-metal. In this case, there is just sharing of electrons to attain a noble gas. So what does a covalent bond comprises of? Is the electrostatic force between A is having a nucleus. The nucleus, we all know a nucleus is positively charged. The electrons are negatively charged. So is the electrostatic attraction between the positive nuclide and a shared pair of electrons, such that the positive nucleus is being attracted to the negatively charged electrons. So that is a covalent bond. So in a covalent bond is simply the sharing of electrons to attain a noble gas stability. At the end of the day, the covalent bond constitutes of the electrostatic force of attraction between the positive nuclide and shared pairs of electrons. Here we have two types of covalent bond. We have a simple covalent bond. So we have a simple covalent bond, simple covalent, simple covalent bond, and what? And dative covalent bond, dative covalent bond. How? Simple covalent bond and dative covalent bond. So actually, we are going to take Roman 1. Roman 1 is a simple covalent bond. Roman 1. Simple covalent bond. In a simple covalent bond, there are couples of compounds. There we are going to illustrate a simple covalent bond. Here we are going to take the molecule of ammonia, water, and methane. Methane. One of the simple covalent bond is between the metal, two non-metals, first of all. That is different between a covalent bond and an ionic bond. For an ionic bond, we're dealing with metals and non-metals. But here, we're dealing with non-metals like nitrogen, hydrogen, oxygen, carbon, hydrogen. All of these elements are non-metal. So in this case, we're not going to see a metal here if we're talking about a covalent bond. So these are examples of compound with simple covalent bond. There are many of them: hydrogen sulfide, carbon dioxide, etc. But what matters here is to know the notion of a covalent bond. And with that notion, you'll be able to draw the covalent bond for other compounds. So let's go straight to the point. We take the molecule of ammonia. So we take the molecule of ammonia. So take the one of ammonia. So ammonia, so whenever they give you this type of compound to do the bonding, so this is what you will do. you can split a compound. You split a compound. Ammonia is made up of one N atom and three H. So you split the compound. Like that, it will be very easy to draw the covalent bondings. You see, the molecule of ammonia is made up of one atom of nitrogen and three atoms of hydrogen, joined together by a covalent bond. So we'll start by writing the electronic configuration. Nitrogen, atomic number is 7. That is 2 is 2. That is 2 is to 5. So that 2 plus 5 is 7. Hydrogen just have one electron in the outer molecule. So in this case, before bondings now, we have one atom of nitrogen combined with 3 atoms of hydrogen. So we have one atom of nitrogen. Having how many electrons in the outer molecule? There are 5 of them. So 1, 2, 3, 4, 5 plus 3 hydrogen atoms. H, 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 X, X, X. You see, each hydrogen atom have one electron in the outer molecule. That is why hydrogen is placed in group 1 of the periodic table, because it just have one electron and one proton. In this case now, each hydrogen atom will bond with one of these electrons of nitrogen. And there are 3 hydrogen atoms. So at the end of the day, we're going to have this. We have nitrogen, so put nitrogen. Then there are 3 hydrogen atoms. So here put H, H, H. 1, 2, 3. So these are the electrons for hydrogen. They will put down the electrons for nitrogen because yes, there is nitrogen, hydrogen, hydrogen. We'll put the electrons for nitrogen now. So we'll put the electrons 1, 2, 3. Put them 1, 2, 3. You see that we have used 3 electrons, 1, 2, 3, and 2 electrons are left. So can we put the 2 electrons here? 1. So we realize that okay, the molecule of ammonia contain 1, 2, 3, 3 bonded pair and 1 lone pair of electrons. So we realize that the electronic configuration for nitrogen goes down to what? 2 is to 8 because there's 5 electrons here. Plus these 3 electrons of hydrogen. We're having 2 is to 8 configuration. We're now going to go straight to the second molecule, the molecule of water. So let's take the molecule of water. So water gives 2H and O. In this case, we write a configuration for oxygen. So here's 1 and 2. Oxygen is 8, that's 2 is to 6. So we'll have the oxygen atom O with 6 electrons in the outermost shell. So we have 6 electrons in the outermost shell for oxygen. So having 1, 2, 3, 4, 5, 6. Plus hydrogen now have just 2 hydrogens for water. H. Here's X. Obviously, it's before bondings. It's before. Every year is before bonding. Before bondings. Yes, after. After bondings. So, in this case now, each of the hydrogen atom will take just 1 electron. So at the end of the day, having oxygen O have H. Remember, the H atom has 1 electron. So put 8 X. So each X goes with 1 dot. Right? That. Well, I've used just 2 dots. 4 dots are left. So I've used just 1, 2. Out of the 6, we're left with 4 dots. So put here 1, 2, 3, 4. Oxygen now tends to its configuration. Yes, after bondings. So we can go to uh, the third molecule, which is the molecule of methane. In this case, we have seen ammonia. So we've seen that ammonia has 3 bonded pair, 1 lone pair of electron. Water has 2 bonded pair, 2 lone pairs of electron. So here are the bonded pair, 1, 2. The lone pairs, 1, 2, because say pair. So the shape of the molecule will be different. That's why we are first of all doing this dot and cross diagram, so that after we are going to see the shapes of molecules. Because the shape of molecule will depend on the number of bonded pair and lone pairs of electrons. Because the shape of ammonia, I doubt if it's going to be the same as that of water. It's impossible. Because they don't have the same number of bonded pair and lone pairs. So now we're going to see the molecule of methane. That will be our Roman 3. Roman 1 was ammonia, that we saw ammonia. Then the second one is water. Then the last one is methane. So we see methane. Methane. So Roman 3 methane. Methane. Methane is CH4. That will give us 1 atom of carbon and 4 hydrogen atoms. Write the electronic configuration for carbon. Carbon is 4. So carbon is atomic number 6. Configuration 2 is to 4. So we have 1 atom of carbon and 4 atoms of hydrogen. So let's do our normal traditional covalent bond. Yes, a simple covalent bond. The simple covalent bond will have the atom of carbon. So here's the atom of carbon. The 4 electrons in the outermost shell. So 1, 2, 3, 4. Electrons occur in 2, 2. That's the duplet rule. Plus the hydrogen, we're having 1 hydrogen, 2, 3, 4 hydrogen atom. X, 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 X. At the end of the day, now we have our carbon atom. So carbon atom. So yes, hydrogen, 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 hydrogen. H, 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 H. X dot, X dot, X dot, X dot. So clearly see that, okay, the hydrogen atom is having just 1 electron in that motion. The carbon atom are having 4. In this case, given that we have 4H and 4 electrons, each of the electrons bond to this electron. That means they pair up together. At the end of the day, we're having what? We're having H, X dot, X dot. So we're having 4 electrons in the outermost shell. In this case, we're having now a molecule with 4 bonded pair and no lone pairs of electrons. So we're going to see now our dative covalent bond, because covalent bonding will say that is divided into 2. We're having our covalent bond divided into 2. What's simple? Comma 1 was simple covalent. Simple covalent. Covalent 2 is dative covalent. Simple covalent. Command 2. Dative covalent. Okay. Let's go down to Roman 2. There's dative covalent bond. In the dative covalent bond now, we'll just have 1 atom, 1 participant atom. So here we'll have dative covalent bond. Dative covalent. In a dative covalent bond, we just have one participant atom that donate the electron, while the other guy receive the electron, which is different from simple covalent bond where both atoms were participating in the covalent bond. But here is different. It's true, you see a sharing is some sort of sharing. Given the covalent bond, we use the word sharing. But the sharing of this guy is different from the other one. So during the dative covalent bond, we just have one participant atom that donate the electron. That means we have two types of atoms here, the donor atom and the acceptor atom. The donor atom donate the electron, the acceptor atom accept the electrons. So what is the physical significance of that? Let's take an example. Example, we can have the case of the ammonium ion, NH4 plus. The ammonium ion now is made up of what? Ammonia plus H plus. So we can dissociate this ion. Ion is made up of ammonia plus H plus. Ammonia is NH3. We saw the bondings for ammonia. H plus means hydrogen has lost its electron because hydrogen has one electron in the outermost shell. So it means that H is different from H plus. So there is H here. H has one electron in the outermost shell. H plus has 0. It has nothing because it has lost its electron. So it means that H plus has an empty orbital. It has a vacant orbital. That means the orbital is empty. In this case, H plus will be the acceptor atom because it has 0 electron. The outermost shell has an empty space where the electron will come and relocate itself. So H plus has an empty orbital. H is having one electron. So let's draw the chemical bonding. So ammonia. So this is the molecule of ammonia, N. Remember what we saw about ammonia? Ammonia has one lone pair of electron. So ammonia with one lone pair of electron. H plus hydrogen. Hydrogen has a vacant orbital. I mean an empty orbital. Hydrogen plus. So here's hydrogen plus here. That's hydrogen plus. So during the dative covalent bond, there will be the transfer of electron from the donor atom, which is nitrogen here. The acceptor atom is hydrogen. So electrons will move from the donor atom, which is N, to the acceptor. At the end of the day now, we're going to have a dative covalent bond. So having N, giving it electrons to H, 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 H plus. Let's say we can have this. At the end of the day, we'll see that there's a dative covalent bond. The dative covalent bond between nitrogen and hydrogen. So that's the difference between a covalent bond, a simple covalent bond, and a dative covalent bond. In a simple covalent bond, there's a sharing of electrons. Electrons are being shared. But in a covalent bond, in a dative covalent bond, now, one atom or one participant atom donates the electron, while the other guy accepts the electrons. Like what happened to the molecule or the ion of NH4 plus. The N atom has lone pair of electrons. This electron are being transferred to the H atom. At the end of the day, you have this molecule. Now we're going to see our last type of chemical bond, which is a metallic bond. Because we said earlier that there are three main types of bonding: ionic bond, covalent bond, and metallic bonds. Under covalent bond, we saw two types. We have simple covalent bond and dative covalent bond. Now we're going to see our last type of chemical bondings, which is, before we see our last type of chemical bondings, let's see the property of covalent compounds first. What are the properties of this compound? Properties of covalent compounds. Properties of covalent compounds. Properties of covalent compounds. Heaven. Covalent compounds, they do not conduct electricity, be it in solution or in a molten state. Why? The covalent compounds actually, they don't have free mobile electrons. They don't have it. They are not like they don't have free mobile ions, just like ionic compounds. But in this case, the electrons are bonded. They are bound, so they do not conduct electricity, be it in a molten or in solution. They do not conduct electricity. The next, they have low melting and boiling point because the atoms are held together by weak covalent bonds. Next, they are soluble or they are soluble in inorganic solvent like methane, like benzene and acetone. So these are quite the properties of these covalent compounds. And we'll now see the metallic bondings. Metallic bondings. C. Metallic bondings. Metallic bondings. So metallic bonds. A metallic bond simply is the electrostatic force of attraction between a positively charged ion and a sea of delocalized electrons. Example, let me take a metal M. Pardon, a metal M. So let me take a metal M with one electron in the outermost shell. So M will give M plus E minus. So M form its ion by losing a single electron because it has one electron in the outermost shell. At the end of the day, we'll have M plus and E minus. So the metallic bond in this case is between this positively charged ion and a sea of delocalized electrons because the electrons are turning round. We have a cloud of electrons turning around the positively charged cations. So the cation is being surrounded by a sea of electrons. The electrons are being attracted to the positively charged cation. We simply means that the electrons are delocalized. So they are delocalized. So the metallic bond, the electrostatic force of attraction between a positively charged cation and a sea of delocalized electrons. So let's take a typical example like we'll take the one of sodium. So sodium. Take the element sodium. Sodium electronic configuration is 2:8. It's to 1. The sodium atom has one electron in the outermost shell. So the one electron will be delocalized in the metallic crystal lattice. In this case, the sodium will give what? Sodium plus E minus. In this case, the metallic bond is between the sodium plus and the sea of electrons. So let's draw the metallic bond itself and actually see what's happening. So we'll have sodium plus, sodium plus, sodium plus, sodium plus, sodium plus, sodium plus. So have, let's say, 3 layers of sodium plus, 3 layers of sodium plus. So you have so we have E minus, E minus, E minus, E minus, E minus, E minus, So that's the meaning of a metallic bond. E minus. So we have positively cation. So here we'll have embedded. So we will have, these are the positive ions that are swimming. We can say they are swimming in a sea of delocalized electrons. They are swimming actually. So actually, these guys are actually swimming a sea. So here we have delocalized electrons. Here we have of cations. So these cations are swimming in a sea of delocalized electrons. So the properties of this compound is obviously the compound will conduct electricity. Why? Because they have free mobile electron. The electron can move from one part to another inside the metallic crystal. So the electrons are free to move in the crystal. So they have free mobile electrons. And also, the metal are malleable and ductile. So they're actually malleable and ductile. Why? Because if you heat, you can easily hammer this sodium metal, or let's say you can have copper or nickel. So metals can easily be hammered, because if you hammer this guy, the electrons can slide against each other. So it can be drawn into wires too. You can actually stretch the elements. They are good conductors of heat and electricity. So they are malleable and ductile. They have high melting and boiling point. Why is that high melting and boiling point? Because you see the bond is actually between the cation and its own electron. So the electrostatic force of attraction is so strong, it will not be easy to break the metallic bond. That is why, in this case, the metallic bond is so strong. That is why the element have high melting and boiling points. So we're done with this first session of we're done with lesson 2, which is type of chemical bondings and their properties. Going on to the second to the last lesson, which is the shape of molecules. So shape of molecules, lesson 3. Shape of molecules. Shape of molecules. Lesson 3. Shape of molecules. Shape of molecules. So we're going to start with the first shape of molecule, which is a linear shape. So linear shape. So have number 1, linear. For us to have the linear compounds, first of all, the linear compound of the form AB2, such that there is no lone pairs of electron. AB2, no lone pairs, no lone pair on the central atom. So that's the condition. The first condition is AB2 and no lone pair on the central atom, because if there's a lone pair of the central atom, we will not be able to have a linear shape. So I'll draw some example of linear molecules. We have the molecule of CO2 is linear, bond angle 180 degrees. We have the one of CO. So the molecule of CO. Sorry, that 1, 1, 2, 3, 4, 5, 6, 7, 8. The one of CO. Then we can have the molecule of BCl2, beryllium, Cl, Cl. But here, the molecule of CO is an exception. It's an exception. Why? Because the molecule of CO have a dative covalent bond. That's a dative covalent bond. So that if you want to count 1, 2, 3, 4, 5, 6, 7, 8, the molecule of CO is an exception. For the typical example, we have the case of beryllium. So BCl2 and CO2. The molecules are linear with bond angle 180 degrees. So our Roman 2 now we're going to see bend or V shape. So bend or V shape. So let's take a typical